script tonight we are going to follow a signal, not a radio signal, not a message from something alive, a different kind. The kind that travels through space as heat, as infrared light too cold and too faint for any human eye to see. The kind that only a satellite in orbit, pointed at the right patch of sky, can detect. And the disturbing part is not that the signal is there. The disturbing part is what happens when scientists try to figure out what is sending it. For nearly a decade, astronomers have been looking for a planet hiding in the outer darkness of our solar system. A world somewhere beyond Neptune, maybe 4 or 5 times the mass of Earth, orbiting so far from the Sun that it takes thousands of years to complete a single lap. They call it Planet 9. They have not seen it. They have not photographed it. No telescope has ever resolved a disk, a surface, a point of light that moves in the way a planet should. But in 2025, researchers published findings from a different kind of search. Not looking for reflected sunlight, because at that distance there is almost none. Looking instead for the faint warmth that even a frozen, distant world radiates into the darkness. And in 40-year-old data, cross-referenced with observations taken 23 years later, a team found something. One object. Moving exactly as slowly as Planet 9 should move. Glowing in exactly the wavelengths where Planet 9 should glow. And then Mike Brown, one of the scientists who originally predicted Planet 9, looked at the orbit, and what he found made the story stranger, not simpler. By the end of tonight, you are going to understand why visible light cannot find Planet 9, how infrared heat signatures work as a detection method, what the 2025 signal actually shows, what Mike Brown found when he ran the orbit calculation, and what the Vera C. Rubin Observatory, now actively surveying the sky, changes about everything. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The outer solar system has always been defined by what we cannot see. For most of human history, the solar system ended at Saturn. That was the limit of the naked eye, the last planet bright enough and close enough to be visible without instruments. Beyond Saturn, darkness, nothing moving, nothing known. Then, in 1781, William Herschel found Uranus. Not because he was looking for a planet, but because he was conducting a systematic survey of the sky and noticed something that moved like a planet. What he initially thought might be a comet turned out to be a world twice the diameter of Earth, orbiting nearly twice as far from the Sun as Saturn. The solar system doubled in radius in a single observation. In 1846, Neptune was found not by observation, but by mathematics. Its gravitational signature in the orbit of Uranus pointed to its existence before any telescope resolved its disk. When the telescope was pointed at the predicted location, Neptune was there. Pluto's discovery in 1930 seemed to extend the solar system further still. But Pluto turned out to be a small, icy world, and in the years after its discovery, almost nothing else was found beyond Neptune for decades. The outer solar system looked sparse, nearly empty beyond a certain distance. That image began to crack in the 1990s. Astronomers started finding more small icy bodies beyond Neptune, first one, then several, then dozens. By the early 2000s, it was clear that the region beyond Neptune contained enormous numbers of these objects, collectively called the Kuiper Belt. The discovery of Sedna in 2003 pushed the known solar system to 84 astronomical units, farther than Neptune by a factor of nearly 3. Then more distant objects followed. Each of these discoveries required new and more sensitive instruments. Each required extending survey programs to cover enough sky and enough depth to find objects that were small, faint, slow-moving, and far away. The history of outer solar system discovery is a history of instruments learning to see fainter things at greater distances. Planet 9, if it exists, represents the next step in that history. It would be the most distant major planet in the solar system. It would also be the first planet found primarily through the gravitational influence it exerts on smaller objects, rather than through a direct sighting. Even Neptune, which was predicted mathematically, was confirmed by direct visual observation almost immediately after the prediction was made. The question of why Planet 9 has not been found, given that the prediction has been in place for nearly a decade, is one that astronomers have had to reckon with seriously. The first answer is the one already discussed: reflected sunlight at those distances is extraordinarily faint. The fourth power law governing reflected light brightness makes the planet's apparent brightness drop off so steeply with distance that even the largest ground-based telescopes face a genuine challenge. The second answer is the size of the search area. Planet 9's predicted orbit covers a vast region of the sky. The refined orbit from 2025 places it at roughly 290 astronomical units on an elliptical path, which means at any given time the planet could be at a wide range of positions along that ellipse. Even after multiple rounds of refinement, the search area remains hundreds to thousands of square degrees of sky. For comparison, the full moon covers about a quarter of a square degree. The Planet 9 search area contains room for thousands to tens of thousands of full moons. Covering that area to sufficient depth, with telescopes that have limited field of view and must share time with many other scientific programs, is a slow process. The Subaru telescope in Hawaii has been used for concentrated Planet 9 searches in the most likely regions. Results have come back with new trans-Neptunian object discoveries, but no Planet 9. The Pan-STARRS survey covered a large fraction of sky at moderate depth, ruling out a planet of certain brightnesses in the regions it covered, but not ruling out all possible positions. Each negative result narrows the search but does not end it. The planet either is not in the surveyed regions to the surveyed depth, or it is at the outer end of the estimated distance range where the survey was not sensitive enough to detect it. Both options are consistent with current data. The third answer is more subtle. The search is being conducted from a moving platform, Earth. The planet moves very slowly, but Earth orbits the Sun every year, and this means the apparent position of a very distant object shifts over the course of a year due to parallax. For Planet 9 at 290 astronomical units, the annual parallax would be roughly 1.2 arc minutes at most. This is small but measurable, and it means that images taken months apart from the same location on Earth will show the planet at slightly different apparent positions even without any actual orbital motion. This helps in confirming moving object candidates, but requires careful bookkeeping when comparing survey data collected at different times of year. The specific region of sky where Planet 9 is most likely to currently reside has been narrowed considerably since the original 2016 prediction. Early predictions placed the most likely sky position near the constellation Orion. Subsequent modelling, incorporating new trans-Neptunian object discoveries and their orbital properties, has shifted the most likely current position to a region that includes parts of Orion, Gemini, Taurus, and northern Eridanus, depending on which orbital solution is used. The fact that the 2025 Fan et al. Candidate was found in Eridanus is notable. Eridanus is a large, sprawling constellation extending from the vicinity of Orion southward across a large area of the southern sky. The location of the candidate in Eridanus is not inconsistent with some of the refined orbital predictions, though the orbital inclination problem remains. What makes the search geometrically difficult is that the region most likely to contain Planet 9 at its current orbital position is large enough that it cannot be covered in a single night of telescope observation, or even a season. Systematic coverage requires either a wide-field survey instrument dedicated to the search over many nights, or an all-sky survey telescope that will cover the region as part of its normal operations. The Vera C. Rubin Observatory, conducting the Legacy Survey of Space and Time starting in 2025, will image the entire accessible sky repeatedly over 10 years. In that process, it will cover the most likely Planet 9 sky positions multiple times per year. The slow motion of Planet 9 against the background of stars, combined with Rubin's ability to detect very faint moving objects by comparing images taken days or weeks apart, makes it an effective Planet 9 hunting instrument. Rubin's 2 gigapixel camera captures an enormous field of view, about 9 square degrees of sky per image. That is equivalent to roughly 36 full moons in a single photograph. Over the course of the 10-year survey, the depth and breadth of coverage will exceed anything previously attempted. If Planet 9 exists and is within the estimated parameter range, Rubin has a strong probability of finding it. The concept of an extreme trans-Neptunian object, the class of bodies whose orbital clustering motivated the Planet 9 prediction, requires some explanation to understand why it is taken so seriously as evidence. Most objects in the Kuiper belt orbit relatively close to the same plane as the known planets, and at relatively modest distances. They have low eccentricities and inclinations, meaning their orbits are fairly circular and close to the ecliptic plane. These are the classical Kuiper belt objects. A subset of objects, however, have orbits that are highly elongated, with semi-major axes exceeding about 150 astronomical units and perihelion distances, their closest approach to the Sun, beyond 30 astronomical units. These are the extreme trans-Neptunian objects. They spend most of their orbital time at enormous distances from the Sun, where the influence of the known planets is negligible. For these objects, the orientation of the elongated part of the orbit in physical space, specifically the direction toward which the elongation points, should in theory be randomly distributed across all possible orientations if there is no special physical influence on them. In the absence of any gravitational shepherd, the orientation should be spread uniformly around the sky. They are not. The known extreme trans-Neptunian objects cluster in a specific direction. Their orbital elongations tend to point in the same general direction in space. Their orbital planes tend to be tilted in similar ways. This is not what random distribution looks like. The statistical significance of this clustering has been evaluated and re-evaluated many times, accounting for the fact that surveys have not covered the sky uniformly, which could artificially create the appearance of clustering if more observations were made in some directions than others. When this observational bias is properly corrected for, the clustering remains. The 2024 analysis that found the Planet 9 free scenario rejected at 5 sigma confidence was specifically designed to address the observational bias concern rigorously. Something appears to be sculpting the orbits of these distant objects. Planet 9 is the leading proposed explanation, an undiscovered planet on a wide, slightly eccentric orbit, tilted modestly from the ecliptic, would gravitationally shepherd extreme trans-Neptunian objects into the clustering pattern observed. This is the same principle by which Neptune sculpts the inner Kuiper belt, organising populations of small bodies into stable orbital niches through repeated gravitational interactions over billions of years. The infrared detection strategy that produced the 2025 candidates uses physics that is worth understanding in more detail. When any object absorbs radiation, it heats up. When it radiates that heat back into space, it does so at a temperature determined by the balance between the energy it absorbs and the energy it emits. For an object far from the Sun, absorbed solar radiation is minimal. The temperature of the object is set by this balance at a very low value. An object at 500 to 700 astronomical units from the Sun would absorb very little solar radiation, but it also has its own internal heat, from the residual warmth of its formation process and from the slow decay of radioactive elements in its rocky interior. For a planet of several Earth masses, this internal heat source is small but real. It prevents the planet from cooling all the way to the temperature of the surrounding space, which is just a few Kelvin above absolute zero, the temperature set by the cosmic microwave background radiation. The result is a planet that sits at a temperature somewhere between the cosmic background temperature and a temperature determined by a tiny amount of solar heating and internal heating. For Planet 9 at the predicted distances and masses, that temperature is estimated at 28 to 53 Kelvin, or roughly negative 220 to negative 245 degrees Celsius. At this temperature, the peak of the object's thermal emission, following the principle described by Wien's law which relates temperature to the wavelength of peak emission, falls in the far infrared range at wavelengths of roughly 55 to 100 micrometers. This is not a wavelength visible to the human eye or to standard photographic instruments. It is detectable only by instruments specifically designed for far infrared astronomy. The IRIS satellite in 1983 and the Akari satellite in 2006 were both sensitive to this wavelength range. They were built for entirely different scientific purposes, not specifically to find Planet 9, which was not even proposed until 2016. But their sky surveys cover the wavelengths where Planet 9's thermal emission would appear, and the 23-year separation between the surveys provides the time baseline needed to detect the slow orbital motion. Using archival data from instruments built for other purposes to search for an object whose existence was predicted decades after the data was collected is a methodologically creative approach. It is also the kind of approach that has occasionally led to important discoveries in astronomy, where the data archive often contains more information than it was originally analysed to provide. The primordial black hole alternative to Planet 9 deserves more careful examination than it usually receives in popular accounts, not because it is likely, but because it illustrates something important about what the gravitational evidence actually says. If a primordial black hole with a mass of 5 to 15 Earth masses exists somewhere in the outer solar system, it would gravitationally affect nearby objects in exactly the same way as a planet of the same mass. The orbital clustering of the extreme trans-Neptunian objects would be produced just as efficiently by a black hole as by a planet. Because gravity does not distinguish between mass organised as a rocky and icy world versus mass compressed to a singularity. The difference is in how we would detect it. A planet reflects sunlight, emits thermal radiation, and can be photographed. A primordial black hole of this mass emits only Hawking radiation, which at this mass scale is at a temperature of roughly a billionth of a Kelvin above absolute zero. The flux of photons from such Hawking radiation is completely undetectable by any current or foreseeable instrument. It would not show up in infrared surveys. However, a primordial black hole in the outer solar system could potentially be detected through gravitational microlensing. If a background star happened to pass behind the black hole as seen from Earth, the black hole's gravity would temporarily magnify the star's light, producing a characteristic brightening and fading pattern. This lensing event would be extremely rare given how few objects in the outer solar system are aligned with background stars at any given time. But dedicated microlensing surveys might in principle accumulate enough observations to either detect such an event or place meaningful limits on the probability. The more immediate difference between the planet and black hole scenarios is in the infrared detection method. If the Fan et al. Candidate or the Chen et al. Candidates are real objects. They are showing thermal emission in the far infrared. A primordial black hole would not produce this emission. A real infrared detection, if confirmed, would effectively rule out the primordial black hole interpretation and point toward a genuine planet. This is one more reason why confirming or ruling out the 2025 infrared candidates through follow-up observations matters for the broader question of what the outer solar system contains. The history of failed Planet 9 detections contains a pattern worth noting. Each time an apparently promising candidate has emerged, the follow-up work has produced either a non-detection when the candidate position is re-examined, or an orbital solution incompatible with what Planet 9 should be. This is not unusual in science at the frontier. In any search for a faint, uncertain object, most candidates will turn out to be something other than what was hoped. What makes the Planet 9 search specifically interesting is that the gravitational evidence, the clustering of extreme trans-Neptunian objects, has not gone away or weakened. It has strengthened with more data. The statistical support for something gravitationally organizing the outer solar system has increased as the catalogue of known objects has grown, and as the analysis has become more sophisticated. In most scientific searches, if the direct detection evidence is absent or contradictory after many years of searching, it begins to erode confidence in the underlying prediction. But the Planet 9 case is unusual, because the indirect evidence, the orbital clustering, is not a one-time observation that might be revised away. It is a systematic pattern that appears across many independent objects discovered by multiple independent surveys using different telescopes and different detection methods. Every new extreme trans-Neptunian object that is discovered either fits the predicted clustering pattern or does not, and the majority have fit it. This creates a situation where the indirect evidence is growing stronger while the direct evidence remains absent. That combination is unusual and genuinely uncomfortable for a field that values direct observation over inference. The 2025 Eris-Akari candidate was the closest thing to direct evidence yet produced, and it failed the orbital test. But the infrared strategy itself is not discredited. The Fan et al. Paper explicitly notes that their one surviving candidate needs follow-up. Confirmation or refutation of that candidate's orbital properties through additional observations that would allow its full orbit to be determined remains an open scientific task. The instruments being brought to bear on the Planet 9 search in the coming years are worth understanding individually, because each one adds a different capability. The Subaru telescope on Mauna Kea in Hawaii has a primary mirror 8, 2 meters across, and is equipped with Hypersuprime Cam, a wide-field mosaic camera covering about 1.8 square degrees of sky per image. The Subaru telescope has been the primary tool for the targeted Planet 9 search led by Batygin and Brown, along with Scott Shepard and Chad Trujillo, who have been conducting independent searches. Its combination of aperture and field of view makes it particularly effective for covering the most likely search regions in the sky, going deep enough to detect a Planet 9 of the predicted brightness. The dark energy camera on the Victor M. Blanco telescope in Chile covers 3 square degrees per image and is one of the most sensitive optical survey cameras in the southern hemisphere. It is the follow-up instrument most frequently cited in papers about outer solar system candidates, because it can quickly cover a candidate's predicted position and either detect the object or rule it out to a specific depth. For the Fan et al., infrared candidates, DE-CAM follow-up would be the natural next step. Observe the candidate positions in optical light and look for a moving object. The James Webb Space Telescope, while primarily designed for deep-field astronomy and galaxy and exoplanet science, has infrared capabilities that could in principle be pointed at high-confidence Planet 9 candidates to characterize them in detail. DREST's sensitivity in the mid-infrared is extraordinary, but its field of view is very small, making it unsuitable for a blind survey. It is a follow-up instrument rather than a discovery tool for this particular search. The combination of Rubin for discovery, Subaru and DE-CAM for targeted follow-up, and potentially DWEST for detailed characterization represents the full toolkit currently available. Each instrument has a role depending on the stage of the search, from initial survey through candidate confirmation to detailed characterization. There is a version of the Planet 9 story where the planet does not exist, and it is important to understand what that would mean. If the Vera C. Rubin Observatory conducts several years of operations, discovers tens of thousands of new trans-Neptunian objects, and does not detect Planet 9, that result would be significant. It would not necessarily disprove the existence of a distant planet, but it would push the allowed parameters into a range where the planet would have to be fainter and farther than current best estimates suggest. A planet that is consistently undetectable by surveys of this depth would have to be either very small, very distant, or on an orbit that has been placed it currently at an unfavourable position near the farthest point in its orbit. If the non-detection continues, the orbital clustering that motivated the prediction would need explanation through other mechanisms. Several alternatives have been proposed. A ring of material distributed at large distances in the outer solar system, without being concentrated into a single massive object, could in principle produce similar orbital clustering through collective gravitational effects. A disk of many small objects, none massive enough to be considered a planet, might produce the same statistical signal as a single large planet. These alternatives have been modelled and generally fit the observations less well than the Planet 9 model, but they have not been ruled out. A sufficiently deep non-detection from Rubin would reinvigorate interest in these alternatives, and would challenge the community to develop better discriminators between the models. The history of science has examples of compelling statistical predictions that turned out to be artifacts. The prediction of Planet X in the early 20th century, which motivated the search that accidentally discovered Pluto, was based on apparent discrepancies in Uranus's and Neptune's orbits that turned out to be measurement errors. When the orbits were recalculated more accurately, the discrepancies disappeared, and the prediction of Planet X was shown to be unfounded. Planet 9 could be a modern version of this story. The statistical clustering could be partly an artifact of survey geometry, partly a chance alignment, partly an incomplete understanding of the gravitational effects of the known giant planets at large distances. The confidence level of the analysis is high, but it is not certainty, and the history of outer planet predictions warrants appropriate humility. The question of what Planet 9 would be physically, if it exists, is one that has been addressed in some detail. Based on the mass range of roughly 4 to 17 Earth masses, Planet 9 would be in the category sometimes called a super-Earth, or mini-Neptune. Below about 10 Earth masses, planets tend to be predominantly rocky with some icy components, like a larger version of Earth, or Uranus in composition, but without Uranus's thick gaseous envelope. Above that range, planets tend to accrete significant hydrogen and helium gas during their formation and become more gas-rich. At 4.4 Earth masses, the 2025 estimate from Siraj et al. Suggests Planet 9 might be closer to the rocky super-Earth end of this spectrum. If it was the core of a giant planet that was ejected before it could accrete much gas, it could be largely rocky and icy, with a thin atmosphere if any. Its surface temperature, around 28 to 53 Kelvin, would make it incomparably colder than any world in the inner solar system. Even Pluto, at roughly 40 astronomical units from the Sun, is warmer than Planet 9 would be at 290 astronomical units. At those temperatures, most of what we would consider volatile gases are frozen solid. Nitrogen, carbon monoxide, methane, all of which exist as gases on Pluto's warmer surface, would be locked in surface ice on Planet 9. The surface would be dark, very little sunlight reaches it, and what little does would be reflected or absorbed by a surface of frozen gases and rock. There would be no wind, no weather driven by solar heating, no liquid anything. The world would be geologically quiet except for the slow interior cooling and the gradual decay of radioactive elements that provides its tiny amount of internal warmth. It would be, in every sense, a frozen relic. A world preserved almost unchanged since its formation and subsequent scattering, carrying in its composition and structure the record of a violent event that occurred 4 billion years ago. The broader implications of finding Planet 9, should it be confirmed, extend beyond the simple addition of a new planet to the catalogue. The existence of a planet mass object at 290 astronomical units on a tilted and eccentric orbit would be compelling evidence for the violent dynamical history of the outer solar system. The current arrangement of the planets, with Jupiter, Saturn, Uranus and Neptune on relatively circular, nearly coplanar orbits, represents a settled state that was reached after a period of much more chaotic interaction in the solar system's first 100 million years or so. Models of early solar system dynamics suggest that the giant planets did not form where they are now. They formed in a more compact configuration and migrated over time through gravitational interactions with the disk of gas and small bodies that surrounded the young sun. This migration was not smooth or gentle. It involved close encounters between giant planet cores, gravitational scattering of small bodies, and possibly the close approach or departure of nearby stars from the Sun's birth cluster. During this period, it is possible, perhaps likely, that the solar system formed additional planet-sized objects that were subsequently ejected to large distances or entirely expelled from the solar system. Some may have become free-floating planets, unbound to any star. Some may have settled into very distant orbits around the Sun, perturbed by the gravitational influence of other early solar system members or nearby stars, but not expelled entirely. Planet 9, if it is real, is a fossil from that epoch. A planet that formed in the warm, dense inner or middle solar system was flung outward and ended up on a stable but distant orbit that preserves information about the conditions of the early solar system that no other current object encodes as well. Finding Planet 9 would not just be finding a new planet, it would be opening a window into the solar system's most violent and formative period, preserved in the orbit of a single frozen world 4 billion years after those events. There is a reason no telescope has directly photographed Planet 9, and it is not simply a matter of needing a bigger telescope. It is a matter of how light works at extreme distances. When you see any object in space by reflected light, that light makes a round trip. It leaves the sun, travels to the object, bounces off the surface, and then travels back to the telescope. The intensity of reflected light follows a specific mathematical rule. Double the distance, and the object becomes 16 times fainter. Not twice as faint, 16 times. The brightness falls off as the fourth power of the distance. Neptune is roughly 30 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun. Planet 9, based on current estimates, is somewhere between 200 and 700 astronomical units away, depending on which calculations you trust. Even at the closest end of that range, it would be around 7 times farther from the Sun than Neptune. 7 times farther means the reflected sunlight at its location is about 50 times weaker than what reaches Neptune, and that already weak light then has to travel back to us, diminishing again. The result is a planet so dim that even the largest telescopes in the world, scanning for hundreds of hours, have difficulty distinguishing it from background noise. This is why optical surveys have consistently failed. The Zwicky Transient Facility searched, the Dark Energy Survey searched, Pan-STARRS searched. All of them covered large fractions of the sky where Planet 9's orbit should place it. All of them came back with no confirmed detection, not because the planet is not there, but because reflected sunlight at those distances is too faint to distinguish from an object of that size. So the question becomes, is there another way to detect it? The orbital dynamics that would produce Planet 9's current situation are worth understanding, because they connect the distant cold darkness where Planet 9 presumably resides to the active, violent inner solar system that Earth inhabits. In the first few 100 million years of the solar system's existence, the giant planets were not where they are now. Computer simulations of early solar system dynamics, particularly the models developed in the early 2000s by researchers at the Observatory of Nice in France, suggest that Jupiter, Saturn, Uranus and Neptune originally formed in a more compact arrangement. They were closer together, closer to the Sun, and surrounded by a massive disk of smaller bodies extending outward. As this period progressed, gravitational interactions between the giant planets and the smaller bodies in the disk caused the planets to migrate. Jupiter moved slightly inward, Saturn, Uranus and Neptune moved outward. This migration was not a smooth drift. It was punctuated by periods of chaotic instability, when the planets' orbits changed rapidly and the smaller bodies were scattered in all directions, some into the inner solar system, some into the outer reaches, and some out of the solar system entirely. During this period, the gravitational energy available from planet-planet interactions was enormous. If a fifth giant planet formed in the same region and had a close gravitational encounter with Jupiter or Saturn during the instability, the outcome could easily have been a rapid change in that fifth planet's orbit, scattering it to a much larger distance. A planet scattered by Jupiter or Saturn from a relatively close orbit to an orbit of hundreds of astronomical units would still be moving fast enough to remain bound to the solar system, just barely. Its new orbit would be highly elongated, taking it far out into the cold darkness on one end and bringing it back relatively close to the Sun on the other. The period would be measured in thousands of years. The semi-major axis, the average of the closest and farthest approach distances, would be several hundred astronomical units. This is precisely the kind of orbit that current models predict for Planet 9. The estimated semi-major axis of around 290 astronomical units with an eccentricity of about 0. 29 implies an orbit that brings the planet as close as about 200 astronomical units at closest approach, and takes it out to roughly 370 astronomical units at its farthest. These numbers are consistent with what you would expect from a planet scattered outward by a gravitational encounter with Jupiter or Saturn, with some subsequent modification of the orbit by external gravitational perturbations. The reason Planet 9's orbit has an inclination of roughly 6 degrees from the solar system plane, rather than being precisely in the plane, is also connected to this formation story. If Planet 9 were scattered purely by a two-body interaction with a giant planet, with no other influences, its orbit would likely remain close to the plane of the solar system. Most of the angular momentum of the solar system is concentrated in the plane of the ecliptic, and gravitational scattering events tend to preserve the orbital plane to some degree. But the early solar system was not just a sun plus planets. It was embedded in a dense stellar environment, the Sun's birth cluster, containing many other stars relatively close together. In the first few tens of millions of years after the Sun formed, before the birth cluster dispersed, nearby stars would have exerted gravitational tidal effects on objects in the outer solar system. These tidal effects could have modified the inclination of Planet 9's orbit, tilting it slightly out of the ecliptic plane. Additionally, if the solar system passed through or near a region of higher stellar density early in its history, passing stars could have gravitationally perturbed Planet 9's orbit, changing both its inclination and the orientation of the elongated part of its orbit. The specific inclination of about 6 degrees predicted by the 2025 orbital analysis is mild enough to be consistent with these kinds of external perturbations, without requiring any particularly dramatic encounter. This mild tilt is actually important for the Planet 9 hypothesis. An orbit tilted 6 degrees from the ecliptic would allow Planet 9 to gravitationally influence the extreme trans-Neptunian objects in the specific way needed to produce the observed orbital clustering. An orbit that was either in the plane or perpendicular to it would produce a different effect. The predicted 6-degree tilt, combined with the orbital eccentricity and semi-major axis, is specifically designed to match the observed clustering pattern. This is why the Brown orbital calculation for the Farn et al. Candidate was so discouraging. An orbit tilted 90 degrees would not produce the clustering that motivated the prediction in the first place. Whatever that infrared source is, it cannot be the gravitational shepherd of the extreme trans-Neptunian objects. The Veressey-Rubin Observatory deserves a fuller description than a brief mention, because it represents a genuinely different class of instrument from anything used previously to search for Planet 9. Its primary mirror is 8.4 meters in diameter. That is large for a survey telescope, which typically trades mirror size for field of view to cover more sky per night. The Rubin telescope uses an unusual tri-lens optical design that provides an exceptionally wide field of view of 9.6 square degrees, combined with the light collecting power of an 8-meter class mirror. No previous telescope has combined aperture and field of view in this way. The camera, known as LSS TCAM, contains 189 individual detector chips, arranged in a mosaic 64 centimeters across. The total pixel count is 3.2 billion. Each image, taken in about 15 seconds of exposure, covers an area of sky about 45 times the size of the full moon, with a depth capable of detecting objects far fainter than any previous sky survey achieved at comparable speed. Over its 10-year program, the Rubin Observatory is expected to photograph the southern sky so many times and with such sensitivity that the catalogue of known solar system objects will be transformed. Currently, roughly 4,000 trans-Neptunian objects are known. Rubin is expected to discover roughly 37,000 more, a tenfold expansion of the catalogue. For Planet 9, the logic is straightforward. Planet 9, if it exists at the estimated parameters, will appear as a slowly moving point of light in multiple Rubin images taken days or weeks apart. The motion will be too slow to identify in a single image, but the systematic comparison of images taken over time, which the Rubin pipeline is specifically designed to do, will reveal moving objects at rates consistent with very distant solar system bodies. Rubin's first light was achieved in 2025, and full science operations are underway. The statistical probability estimate of a 70 to 80% chance of detecting Planet 9 within the survey assumes the planet is at the orbital parameters currently estimated. If it is farther away than expected, the probability drops. If it is on a more favourable part of its orbit, currently at or near its closest approach to the Sun, the probability is higher. Within the next 2 to 5 years, the Rubin Observatory should either detect Planet 9 or produce a non-detection so deep that it will force a fundamental revision of the orbital predictions. The scientific implications of a confirmed Planet 9 detection extend into several fields beyond planetary science. For the study of solar system formation, it would provide direct evidence for the dynamical instability models that predict a fifth giant planet was ejected during the early solar system. These models have been developed and refined over many years, but they have not had direct observational confirmation of an ejected planet. Planet 9, if found on a scattered orbit consistent with giant planet ejection, would provide that confirmation. For astrobiology, the implications are more indirect but interesting. The structure of the outer solar system affects the delivery of comets to the inner solar system. A distant massive planet in an eccentric orbit would modify the flux of comets coming from the outer reservoirs into the inner solar system over time. A higher comet flux in the past could have delivered water and organic molecules to early Earth. A lower flux in a different period could have reduced the impact rate and allowed life to persist through periods that might otherwise have been more challenging. Understanding the outer solar system architecture more completely would help constrain models of how life's raw materials arrived on Earth. For the study of other planetary systems, finding a planet in a scattered orbit at 290 astronomical units would confirm that this kind of architecture is possible. We have found exoplanets on wide orbits around other stars, but the mechanisms that produce them are debated. Confirming that our own solar system has a scattered planet at these distances would provide a nearby, detailed example of a planetary scattering event that could be studied more thoroughly than any exoplanet system. And for the fundamental question of how many planets a solar system can have, it would change the accounting. A solar system that appears to have 8 planets and actually has 9, one of them hiding at enormous distances, raises the question of how many planetary systems might have additional members we have not yet found. The Fan et al. 2025 paper contains a specific technical detail worth understanding: the use of the Akari monthly unconfirmed source list. The standard catalogues from any sky survey contain sources that were detected multiple times and confirmed through careful analysis. These are the robust, reliable detections. But Akari also maintained a secondary list of sources that appeared to be detected in the data, but did not meet the full confirmation criteria for inclusion in the main catalogue. Sources that appeared briefly, or that appeared in scans taken hours apart but not in scans taken months apart, went into this secondary list rather than being simply discarded. Planet 9, at 500 to 700 astronomical units, would move too slowly to shift significantly in position over the hours that Akari spent scanning the same region of sky in a single observing sequence. But over months, it would shift by enough to not appear in exactly the same position in a repeat observation. This makes Planet 9 specifically difficult to detect in the standard catalogue. It might appear in observations taken hours apart, but fail the confirmation step that requires appearing in the same position months later. The Akari monthly unconfirmed source list was therefore more suitable for this search than the standard catalogue. It contains detections that pass the hourly consistency test, but not the monthly one, which is precisely the signature expected from a very slowly moving solar system object at extreme distances. Using this secondary list, combined with careful cross-referencing with the IRAS primary catalogue from 1983, and applying the expected motion and flux criteria for Planet 9, the Fan et al. Team identified their candidate. The candidate appeared in the Akari monthly unconfirmed list, not in the standard Akari catalogue. For exactly the reason expected, it shifted position enough between monthly observations to be classified as unconfirmed, but not so much as to be identified as a rapid mover. This methodological choice was well reasoned and is part of why the study was published in a peer-reviewed journal. The approach was specifically designed to overcome the limitations that would cause a slowly moving distant planet to fall through the cracks of standard catalogue analysis. Every object with a temperature above absolute zero emits radiation. Even an ice-cold, frozen world in the outer darkness of the solar system, hundreds of astronomical units from the Sun, is slightly warmer than the empty space around it. Not from sunlight, which barely reaches it, but from the remnant heat of its own formation billions of years ago, slowly radiating away into the void, and from a small but real contribution of radioactive decay in its rocky core. Planet 9, if it exists, is estimated to have a surface temperature somewhere between 28 and 53 Kelvin. To put that in terms you can feel, absolute zero, the complete absence of thermal motion, is 0 Kelvin. The coldest temperature ever recorded on Earth's surface is around 184 Kelvin. Planet 9 is expected to be 3 to 6 times colder than the coldest place on Earth. It would freeze oxygen solid, it would freeze nitrogen solid, it would freeze carbon dioxide so completely that the concept of a gas would not apply. But cold is not the same as nothing. At that temperature, an object the mass of several Earths would radiate energy in the far infrared range. Not visible light, not even the near infrared that cameras can sometimes capture. Far infrared, with wavelengths around 65 to 90 micrometers. This is the part of the electromagnetic spectrum associated with the gentle warmth of objects that are cold by any human standard, but still warmer than empty space. Far infrared radiation does not penetrate Earth's atmosphere well. To detect it from the ground, you would need to be above most of the atmosphere, or ideally above all of it. You need a space telescope, and this is where the story of the 2025 signals begins. The Infrared Astronomical Satellite launched in 1983. IRAS, as it was called, spent about 10 months in orbit before its coolant ran out, and in that time it conducted the first all-sky survey in the far infrared. It catalogued hundreds of thousands of sources. Galaxies, star-forming regions, cold dust clouds, asteroids, and presumably, if Planet 9 happened to be in its field of view, a slow moving point of far infrared light at a location nobody at the time would have thought to look for. In 2006, Japan launched a satellite called Akari, which means light in Japanese. Akari conducted a more sensitive all-sky survey in the infrared between 2006 and 2007, with detection limits deeper than IRA's in many wavelength bands. The two surveys are separated by approximately 23 years. Here is why that matters. Planet 9, at its expected distance, moves extraordinarily slowly across the sky as seen from Earth, not because it is moving slowly in absolute terms, but because it is so far away that even substantial physical motion translates into a tiny apparent shift against the background of stars. In 23 years, Planet 9 is expected to shift by roughly 3 arc-minutes per year, which over that full span amounts to something around 40 to 70 arc-minutes of total angular displacement. An arc-minute is 1/60th of a degree. The full moon spans about 30 arc-minutes across. So the expected shift of Planet 9 over 23 years is roughly the width of 1 to 2 full moons on the sky. Tiny from an observational standpoint, but measurable if you are looking for it carefully. A team led by Terry Long Phan at National Chungcheong University in Taiwan, working with colleagues in Japan and Australia, designed a search specifically around this approach. Find every far infrared source detected by IRAS. Find every far infrared source detected by Akari. Look for cases where a source appears at one position in 1983 and at a different position in 2006, with the angular shift in the right range and the brightness in the right range for a distant cold planet. They started with over 2 million sources combined. They applied filters for position shift, for brightness, for spectral characteristics. They worked their way down to 13 candidate pairs. Then they examined the actual images manually, one by one. At the end of that process, one candidate survived. The surviving candidate was found in the direction of the constellation Eridanus. In the IRAS data from 1983, there was a faint infrared source at a particular location. In the Akari data from 2006, that source was no longer at that location, but at a position approximately 47 arc-minutes away in the direction consistent with Planet 9's expected orbital motion. Akari detected a faint infrared source. The same brightness, the same spectral signature across the wavelength bands observed. The researchers estimated the candidate's distance at somewhere between 500 and 700 astronomical units from the Sun. That would place it well beyond the outer edge of the Kuiper Belt, in the cold, dark space where Planet 9 is expected to reside. The inferred temperature from the infrared emission was consistent with the range predicted for a frozen world at that distance. The inferred mass, from the brightness and distance, fell between 7 and 17 Earth masses. All of this was consistent with Planet 9. The paper was published in April 2025. It was peer-reviewed. It was careful. The authors were explicit that this was one candidate, not a confirmed detection. They called for follow-up observations using the Dark Energy Camera in Chile, an instrument sensitive enough to potentially image the candidate directly in visible light and confirm its motion. The astronomical community paid attention, not because the case was airtight, but because this was the most concrete single candidate to emerge from years of searching. And then Mike Brown looked at the orbit. Mike Brown is the astronomer who, with Konstantin Batygin, first proposed the existence of Planet 9 in 2016. He is also the person who discovered Eris, the large trans-Neptunian object whose existence helped trigger the reclassification of Pluto. He has spent the better part of a decade building the theoretical model for what Planet 9 should be, where it should be, and how it should behave. When the Phan et al. Candidate was published, Brown calculated what orbit an object at the candidate's apparent position and apparent motion would need to follow. The answer was unexpected. For an object at the distance and angular shift described in the paper to be Planet 9, it would need to be on an orbit tilted approximately 90 degrees from the plane of the solar system. The solar system's planets all orbit within a relatively flat plane, the ecliptic. Planet 9. To explain the orbital clustering of the extreme trans-Neptunian objects that motivated the original prediction, needs to have an orbit tilted roughly 15 to 20 degrees from that plane. Not exactly in the plane, but close to it. An orbit tilted 90 degrees would be nearly perpendicular to the solar system disk. An object on such an orbit would be crossing the plane of the planets at steep angles twice per orbit. It would have a fundamentally different gravitational influence on the outer solar system than the Planet 9 that the orbital clustering data requires. Brown's assessment, shared publicly and clearly, was that the Fan et al. Candidate cannot be Planet 9 in the form the theory predicts. Whatever the infrared signal represents, if it is a real moving object at the distance claimed, it is probably not the planet the search was looking for. The candidate might be something else. A distant trans-Neptunian object of some kind. A background galaxy with unusual properties. An artifact of the data. Without follow-up observations, the nature of the candidate remains open. But the most tantalizing Planet 9 candidate of the decade failed its first orbital test. The psychological experience of the Planet 9 search from inside the scientific community is worth describing. Konstantin Batygin, who with Mike Brown developed the original prediction, has spoken publicly about what it is like to have proposed a planet that cannot be found. In interviews over the years, he has consistently maintained that the statistical evidence for Planet 9 is stronger now than it was in 2016. He points to the growing catalogue of extreme trans-Neptunian objects, the refined statistical analysis, the models that continue to match observations better with Planet 9 than without. But he also acknowledges that the absence of a direct detection is genuinely puzzling. A planet of the predicted size, at the predicted distance, should be within the reach of existing surveys if the orbital parameters are roughly correct. The fact that it has not appeared suggests either that the parameters are off in some way, or that the planet is currently in a particularly unfavourable position where it is fainter or better hidden than average. Mike Brown has expressed similar persistence, along with a candid acknowledgement that he expected the planet to be found much sooner. The analogy to Neptune, found immediately after the prediction, made initial estimates of the search time optimistic. Neptune was close enough to be found quickly with the telescopes of 1846. Planet 9 is far enough away that even the best current instruments need to cover an enormous area of sky to the necessary depth. The Fan et al. Result illustrates the emotional arc of this kind of search. A candidate emerges. It matches the expected properties in infrared brightness, distance, and apparent motion. The community pays attention. And then the orbital calculation comes back wrong. The disappointment is real but not unexpected. In a search of this kind, most candidates will fail their first test. The question is whether any will eventually pass all the tests. The connection between Planet 9 and the stability of the Oort cloud is an aspect of the science that is less well known but genuinely important. The Oort cloud is a vast, diffuse spherical shell of icy bodies extending from roughly 2,000 to perhaps 100,000 astronomical units from the Sun. It is the source of long-period comets, those that enter the inner solar system on orbits taking thousands or millions of years to complete. The Oort cloud is thought to contain trillions of objects, though this is inferred entirely from the comets it sends our way, rather than from direct observation of the cloud itself. The inner edge of the Oort cloud, the region where the cloud transitions from a more or less spherical distribution to the scattered disk of the Kuiper belt, is not well understood. Objects like Sedna, with a perihelion of 76 astronomical units, occupy a zone that is neither clearly in the Kuiper belt nor clearly in the inner Oort cloud. They seem to be in an intermediate region that has been dynamically sculpted by processes that are not yet fully understood. Planet 9, in some models, could play a role in the dynamics of this intermediate zone. A planet at 290 astronomical units with some orbital eccentricity would gravitationally interact with objects in the region between 100 and 400 astronomical units, potentially explaining why certain objects of perihelia raised above the zone where Neptune's gravity is dominant. Sedna's perihelion of 76 astronomical units is too high to have been placed there by Neptune's gravitational influence alone. Planet 9, if real, might be responsible. This is one of the most compelling aspects of the Planet 9 hypothesis. It does not just explain one anomalous observation. It provides a single mechanism that can account for several different puzzling features of the outer solar system, from the orbital clustering of extreme trans-Neptunian objects to the elevated perihelia of objects like Sedna, to the existence of objects with orbital planes tilted steeply from the ecliptic. All of these features can be produced by a single planet on a slightly tilted, moderately eccentric orbit at a few hundred astronomical units. This explanatory breadth is what gives the hypothesis its staying power, despite the absence of a direct detection. The Siraj, Scheiber and Tremaine 2025 paper that refined Planet 9's orbital parameters deserves specific attention, because it represents the most comprehensive dynamical analysis of the question yet published. The team used a catalogue of 51 extreme trans-Neptunian objects with semi-major axes greater than 150 astronomical units. This is a substantially larger sample than the 6 objects used in the original 2016 prediction, and includes objects discovered in the intervening 9 years by multiple surveys. More objects means more statistical power. With 51 objects showing the orbital clustering pattern, the probability that the clustering is a coincidence is lower than it was with 6. The team ran 300 N-body simulations, numerical computations that integrate the gravitational equations of motion for many objects simultaneously over long time periods. Each simulation started with Planet 9 at a specific combination of mass, semi-major axis, and orbital shape, and evolved the system over billions of years to see what distribution of trans-Neptunian object orbits would result. The best match to the observed distribution of extreme trans-Neptunian objects came from a Planet 9 with a semi-major axis of 290 astronomical units, plus or minus about 30 astronomical units. This is the distance at which Planet 9's gravitational influence, averaged over its orbit and projected over billions of years, produces the specific clustering pattern seen in the data. The mass estimate of roughly 4.4 Earth masses is somewhat lower than earlier estimates. This is significant because a lower mass means a lower infrared luminosity and a lower reflected light brightness. A smaller, lower mass planet at 290 astronomical units is harder to detect than a larger one. The reduced mass estimate is one reason why the search has been difficult and why previous surveys have not found it. The 2025 orbital analysis also notes that at 290 astronomical units, Planet 9 would fall within the search area of the Rubin Observatory's early operations. This timing alignment between the refined orbital prediction and the observatory's commencement of full operations is one reason for cautious optimism in the Planet 9 searching community. This is the disturbing part, and it is worth sitting with. The search for Planet 9 has now lasted nearly a decade. The prediction made by Batygin and Brown in 2016 was compelling. The statistical argument that the orbital clustering of the most distant trans-Neptunian objects would be extraordinarily unlikely without some gravitational influence has been refined and strengthened over the years. The 2024 analysis comparing models with and without Planet 9 found that the Planet 9 free model was rejected at high statistical significance when accounting for the full population of known distant objects. The theory has become more robust, not less, as more data has come in. And yet, the planet itself remains unseen. Every direct search has come up empty. The most promising signal in the far infrared turns out to be on the wrong orbit. The solar system keeps hiding something, or appearing to hide something, and every time astronomers think they are close, the trail leads somewhere unexpected. A second independent infrared study, published by Amos Chen and colleagues in June 2025, using the Akari All-Sky Survey alone, added further candidates but with the same uncertainty. More infrared sources in the right part of the sky, with properties consistent with a distant cold planet. None confirmed. All requiring follow-up observations that take time to schedule, execute, and analyze. Meanwhile, the orbit model for Planet 9 has been revised significantly in 2025. A study by Siraj, Chaiba, and Tremaine, using an expanded catalogue of 51 extreme trans-Neptunian objects and 300 N-body simulations, found that the best fit orbit for Planet 9 has a semi-major axis of around 290 astronomical units. This is considerably closer than some earlier estimates, which had placed the orbit as far as 700 astronomical units. The new estimate puts Planet 9 on an orbit with an eccentricity of about 0.29 and an inclination of roughly 6 degrees from the ecliptic. A planet at 290 astronomical units is still 10 times farther from the Sun than Neptune, still extraordinarily difficult to detect in reflected light. But it is also closer than many previous models suggested, which has two important implications. First, it should be slightly brighter. Second, it falls within the region of sky that the Vera C. Rubin Observatory can now cover. The Vera C. Rubin Observatory in the mountains of Chile achieved first light in 2025. This is a telescope with a mirror 8.4 meters across and a camera containing 3.2 billion pixels, the largest digital camera ever built. Over the next decade, it will photograph the entire visible southern sky every few nights as part of a program called the Legacy Survey of Space and Time. Every clear night, it will go deeper and wider than any previous sky survey. Over that decade, it is expected to discover roughly 37,000 new trans-Neptunian objects, expanding the known catalogue by a factor of 10. Simulations suggest the Rubin Observatory has a 70 to 80% probability of detecting Planet 9 directly if it exists at the orbital parameters currently estimated. Not at the end of the decade. Potentially within the first year or two of full operations. This is a significant statement. For most of Planet 9's history as a theoretical prediction, it has been a hypothesis awaiting an instrument powerful enough to test it definitively. The Vera C. Rubin Observatory may be that instrument. If Planet 9 is at 290 astronomical units on an orbit with a 6-degree inclination, Rubin will likely see it. The planet would be faint but within the reach of a survey camera of this sensitivity. Repeated imaging over months would reveal its slow motion against the background of stars, confirming its nature and allowing its orbit to be calculated precisely. If Planet 9 is not detected by Rubin over multiple years of full operations, that absence will itself be significant. A non-detection at Rubin's sensitivity levels would either require Planet 9 to be considerably farther away than current estimates suggest, or it would raise serious questions about whether the orbital clustering of trans-Neptunian objects requires a planet at all. Either result will change what we think we know. It is worth understanding why the infrared search strategy, despite the Farn et al. Candidate's orbital problem remains one of the most promising approaches. The fundamental issue with optical planet searching is the inverse fourth power law. Reflected light diminishes as the distance to the fourth power, but thermal emission, the infrared glow from a planet's own warmth, diminishes only as the square of the distance from the observer. An object that is twice as far away is 4 times dimmer in thermal emission, not 16 times dimmer. At the extreme distances where Planet 9 is expected to orbit, this difference becomes decisive. The thermal emission from Planet 9 at 290 to 700 astronomical units is many times brighter relative to the background than its reflected sunlight would be. This is precisely why the IRAS and Akari surveys are useful. They were designed to capture far infrared emission, and even though they are old data collected by instruments with limited sensitivity by modern standards, the physics of thermal emission gives them an advantage that modern optical surveys lack. A dedicated far infrared space mission, pointed at the right part of the sky with modern detector technology, could potentially resolve the Planet 9 question definitively through thermal emission, even if optical surveys struggle. No such mission is currently approved, but the concept has been discussed in planning documents for future space observatories. For now, the infrared search strategy consists of mining archival data from IRAS and Akari, both of which are complete but limited in sensitivity. The next generation of infrared space telescopes, if pointed at the appropriate sky region, could push the thermal emission search far deeper than any current or archive data allows. The wider context of these searches involves a puzzle that has deepened, not simplified, over the years. When Batygin and Brown published their original analysis in 2016, they identified 6 objects in the outer solar system whose orbits were clustered in a way that seemed statistically improbable without some external gravitational influence. That finding was immediately controversial, partly because 6 objects is a small statistical sample, and partly because the survey that found those objects had not covered the sky uniformly. In the years since, the catalogue of extreme trans-Neptunian objects has grown. The statistical analysis has been refined to account for observational biases, and the conclusion has held. In 2024, a comparison of dynamical models with and without Planet 9, using the full known population of distant Kuiper Belt objects, found that the model without Planet 9 was rejected at about a 5 sigma confidence level. In statistics, 5 sigma is the threshold conventionally used in physics to declare a discovery. The orbital clustering, adjusted for observation bias, is nearly as statistically significant as many confirmed discoveries in particle physics. But statistical significance is not the same as detection. There could be other explanations. A ring of material distributed through the outer solar system at certain distances could produce similar orbital clustering through collective gravitational effects. A close encounter with a passing star early in the solar system's history could have sculpted these orbits through a single gravitational interaction rather than through the ongoing influence of a planet. These alternatives are less elegant and less consistent with the full range of data, but they have not been ruled out. What can be said is that the evidence for something unusual in the outer solar system is stronger now than it was in 2016. Whether that something is a planet is the question that current searches are trying to answer. The history of predicting planets before seeing them is one of the more instructive stories in astronomy. In the early 19th century, Uranus was behaving strangely. Its position in the sky was not matching the predictions of gravitational calculations based on the known solar system. The orbit kept drifting from where the equations said it should be. Astronomers faced two possibilities: either the equations were wrong, or there was something out there pulling on Uranus that no one had accounted for. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where an unseen planet would need to be to produce Uranus's observed orbital drift. Both arrived at similar predictions. On September 23, 1846, astronomers at the Berlin Observatory pointed a telescope at Le Verrier's predicted location and found Neptune within 1 degree of where it was supposed to be. The parallel to Planet 9 is deliberate and acknowledged by Batygin and Brown. The method is the same: observe gravitational anomalies in known objects, calculate what unseen body could produce them, predict where it should be. Neptune was found almost immediately after the prediction was made, within a single observing session. Planet 9 has not been found in nearly 10 years of searching. This either means the planet is in a part of the sky that has not yet been covered with sufficient depth, which is possible given the enormous search area, or that the analogy is imperfect in some way. Perhaps the trans-Neptunian object clustering has a different cause. Perhaps Planet 9 is significantly farther or fainter than the best current estimates. Perhaps it is at a position that the available telescopes have been looking past rather than at. The history of Neptune is both encouraging and sobering. Encouraging because prediction-based planet discovery has worked before. Sobering because Neptune was found almost immediately, and Planet 9 has not been. Among the alternative theories for what might be causing the orbital clustering, one of the stranger proposals comes from physics rather than planetary science. In 2020, a paper by Jakob Scholz and James Unwin proposed that instead of a planet, what might be orbiting the outer solar system at Planet 9's predicted location is a primordial black hole. Primordial black holes are a hypothetical class of black holes not formed from stellar collapse, but from density fluctuations in the very early universe, in the first seconds after the Big Bang. A primordial black hole with 5 to 15 Earth masses would be extraordinarily small physically, perhaps the size of a large marble or a tennis ball, while containing the mass of several planets. It would exert the same gravitational influence on surrounding objects as a planet of equivalent mass. From a dynamical standpoint, from the perspective of the outer solar system's orbital structure, it would be indistinguishable from Planet 9, but it would be invisible in reflected light because it has no surface to reflect light from. It would emit radiation only through Hawking radiation, a quantum effect so faint at this mass scale as to be completely undetectable by any current instrument. It would show up in gravitational lensing searches if something happened to pass in front of a background star while the black hole was nearby, a chance alignment that could be sought in long-running photometric surveys. The primordial black hole hypothesis is not the consensus view. Most astronomers consider Planet 9 far more likely to be a planet than a black hole. But the proposal illustrates how open the question is, and how unusual an object the outer solar system might be harboring if the gravitational signal is real. The 2025 Akari-based follow-up search by Chen et al. Used a different approach from the Farn et al. Study focusing specifically on the Akari All-Sky survey data rather than cross-referencing with IRAS. The Akari single scan detection list, which captures sources seen multiple times over hours, but not confirmed over months, is particularly suited to identifying slowly moving objects that would shift position between separate observing runs within the same survey. This approach found additional Planet 9 candidates requiring follow-up. Each candidate represents a detection of something faint and moving in the far infrared at a rate consistent with a very distant solar system object. None has been confirmed as Planet 9. None has had its orbit calculated with sufficient precision to either match or contradict the theoretical prediction. What these studies collectively represent is the transition of the Planet 9 search from primarily optical, reflected light surveys to a diversified approach incorporating far infrared thermal emission, archival cross-matching, and new observational methods. The thermal emission approach has now produced specific candidates for the first time. The fact that those candidates have not yet been confirmed does not mean the strategy is wrong. It means the follow-up process takes time. The follow-up observations themselves require scheduling at major observatories with demanding time allocation processes. The DE-CAM on the Victor M. Blanco telescope in Chile is one of the primary candidates for confirming or refuting the infrared detections. But securing telescope time for a target that is currently classified as an unconfirmed candidate requires competing with many other projects for a limited resource. If any of the 2025 infrared candidates is confirmed as a real moving object in the outer solar system through follow-up imaging, the orbital calculation will immediately determine whether it is consistent with Planet 9. That determination could come quickly once the observations are made. There is something worth sitting with about the timeline of this search and what it reveals about the pace of scientific discovery in the deep outer solar system. Human beings have been aware of the planets visible to the naked eye for as long as we have been looking at the sky. The outer limits of the known solar system expanded slowly. Uranus was discovered in 1781, Neptune in 1846, Pluto in 1930. The first Kuiper belt object beyond Pluto in 1992, Sedna in the distant scattered disk in 2003. Each expansion of the known solar system required new technology, new survey methods, and new theoretical frameworks to make sense of what was found. Planet 9 represents a different kind of discovery in progress. Not a chance encounter with something unexpected, but a careful, mathematically motivated search for an object whose existence is predicted by the behavior of other things. The search is informed by theory in a way that most historical planet discoveries were not. And yet the object remains elusive. In a solar system that human beings have been observing with telescopes for 4 centuries, in a sky that has been photographed millions of times, in a universe that we can study with instruments sensitive to radiation of every wavelength, there may be a planet orbiting quietly at the edge of our own home system that we simply have not managed to locate. The infrared signals from the IRAS and Akari data are the most recent chapter in this search. They are promising enough to take seriously and uncertain enough to require more work. The Vera C. Rubin Observatory, now active, represents the best current hope for a direct visual detection. The answer is close. It may arrive in years, not decades. But the outer solar system has been keeping its secrets for a long time, and it is not finished yet. What the 2025 infrared signals tell us, even if they turn out not to be Planet 9, is that the far outer solar system is not empty of detectable things. There are objects out there in the far darkness, moving slowly, glowing faintly in infrared wavelengths that old satellites captured by accident during surveys designed for entirely different science. The archive is large, and the analysis is only beginning. Every passing year adds more objects to the catalogue of extreme trans-Neptunian bodies. Every new survey covers more of the predicted search area. Every refined orbital analysis produces more specific predictions for where the planet should currently be. The target is getting smaller, the instruments are getting better, and the data, from satellite archives and modern ground-based observatories and a new generation of sky surveys, is accumulating faster than at any previous point in this search. There is one more thing to understand about why this matters beyond the scientific question. If Planet 9 is real, it is not simply an additional entry in the catalogue of known solar system bodies. It is evidence that the history of our solar system was more violent and more dramatic than the neat arrangement of planets we see today suggests. The most likely origin story, in Batygin and Brown's own analysis, is that Planet 9 was not born where it lives now. It formed closer to the Sun in the inner or middle solar system, during the chaotic early period when the giant planets were migrating. At some point during that migration, it had a close gravitational encounter with Jupiter or Saturn. The interaction flung it outward to an enormous distance, but it did not escape the solar system entirely. Instead, its orbit was gradually circularized by some combination of gravitational effects, possibly from the Sun's original birth cluster of stars before they dispersed, leaving Planet 9 on a wide but stable orbit thousands of times farther from the Sun than Earth. If this is what happened, Planet 9 is a survivor of the most violent epoch in the solar system's history. A world that formed in the warmth of the early inner system was ejected to the cold outer darkness, and has been orbiting there ever since, for 4 billion years, unseen and undetected, while life developed on Earth, while species rose and fell, while humans built telescopes and started wondering whether there was something else out there in the dark. The infrared signals from 2025 may or may not be Planet 9. The orbital test has already failed once. More tests are coming, but something is out there at the edge of the solar system that we do not fully understand. The gravitational evidence for that is stronger now than ever, and the search has entered its most capable phase. Among the things that would change if Planet 9 were confirmed, one of the most significant is how we describe the solar system to future generations. The current model is 8 planets in a relatively compact arrangement, extending out to about 30 astronomical units, where Neptune completes the known family. Beyond that is the Kuiper belt, diffuse and irregular, populated by small icy worlds rather than true planets. A confirmed Planet 9 at 290 astronomical units would add a 9th planet at roughly 10 times Neptune's distance, extending the planetary solar system to a scale that makes the compact inner 8 planets look like a small inner core. The solar system would be seen as having 2 distinct regions, the known planetary zone from Mercury to Neptune, extending to 30 astronomical units, and then a vast outer region, 40 times wider, where a single cold, isolated planet orbits in nearly complete darkness. The distances involved resist easy intuition. If you built a scale model of the solar system where Neptune were 1 meter from the Sun, Planet 9 at 290 astronomical units would be roughly 10 meters away. The nearest star would be about 3 kilometers. The solar system would turn out to be much larger relative to its immediate stellar neighborhood than the scale models in science museums suggest. This rescaling would affect how we think about the habitability of the solar system over time. The giant planets, particularly Jupiter and Saturn, have played a role in deflecting comets and asteroids away from the inner solar system, reducing the impact rate on Earth, and possibly contributing to the stability that has allowed life to persist here for billions of years. A 9th planet at 290 astronomical units would have its own gravitational influence on the comet reservoir in the Oort cloud and scattered disk, potentially modifying the long-term flux of comets coming into the inner system. Whether this influence has been protective or harmful to life on Earth over geological time is a question that only a confirmed detection would allow researchers to calculate. The 2023 discovery of the object, designated 2023 KQ-14, nicknamed Ammonite by its discoverers, added a specific new element to the Planet 9 picture in 2025. Ammonite is a Sedna-like object, meaning it has a high perihelion distance that places it above the region where Neptune's gravity dominates. Its most notable feature is the orientation of its orbit in space. Its perihelion longitude lies in the direction roughly opposite to the perihelia of other known sednoids and extreme trans-Neptunian objects. The known extreme trans-Neptunian objects cluster their perihelia in one general direction in space. This clustering is the core observational signal for Planet 9. But the clustering was not complete. There appeared to be a gap, a region of sky where no extreme trans-Neptunian objects had their closest approach to the Sun. Ammonite fills that gap. Its orbit, combined with dynamical simulations showing it is stable over the age of the solar system, is more consistent with a Planet 9 orbit at larger distances, around 500 astronomical units, than with the closer configuration of 290 astronomical units. This introduces tension in the Planet 9 parameter space. The Siraj et al. 2025 analysis using the catalogue of 51 objects favours a closer, less massive planet. The Ammonite dynamics favour a more distant, possibly more massive configuration. These are not necessarily irreconcilable, since the uncertainties in the orbital parameters remain substantial, but the discrepancy illustrates that even as the evidence for some kind of outer planet strengthens, the precise properties of that planet are still being argued over. What Ammonite confirms is that the outer solar system contains objects whose orbits are inconsistent with a simple model of 8 planets plus a random background. It adds another data point that something is shaping orbital architecture at large distances. The precise nature of that something remains the open question. The long arc of outer solar system discovery has a quality that is easy to miss when focusing on the specific drama of the Planet 9 search. Every expansion of the known solar system has been followed by a period of adjustment, in which the new understanding overturned assumptions that had been held with great confidence. The discovery of Neptune showed that the solar system was larger than thought. The discovery of the Kuiper Belt showed that the solar system contained vastly more objects than the planet-centric model suggested. The discovery of Sedna and its relatives showed that the outer solar system had structure at distances where nothing was expected. Each discovery required both new instruments and new theoretical frameworks. It was not enough to have better telescopes. Scientists also had to develop new ways of thinking about what they might find. The NICE model, which explained the Kuiper Belt structure through planetary migration, required imagining a solar system history very different from the one assumed for most of the 20th century. Planet 9, if found, would require another such adjustment. Not just the addition of a planet, but a rethinking of the early solar system's dynamics, the history of the giant planets, and the current population of bodies at all distances from the Sun. The outer solar system would emerge as a more complex, more historically layered system than it currently appears. And if Planet 9 is not found, despite exhaustive searches with the most powerful instruments available, that non-detection would also require a new theoretical framework. Something else would need to explain the orbital clustering that the planet was invented to account for. New physics, or new dynamics, or a better understanding of observational bias would need to be developed to close the question. Either way, the outer solar system is not finished surprising us. the current state of the Planet 9 search as of mid-2025 can be summarized as follows. The gravitational evidence for Planet 9, based on the orbital clustering of extreme trans-Neptunian objects, is stronger than at any previous time. The Planet 9 free model has been rejected at high statistical confidence in the most recent comprehensive analysis. The orbital parameters of the planet have been refined to a semi-major axis of approximately 290 astronomical units, with moderate eccentricity and low inclination, making it closer and therefore potentially somewhat easier to detect than earlier estimates suggested. 2 independent infrared search studies published in 2025 have produced candidates that could be consistent with Planet 9's thermal emission, but neither candidate has been confirmed through follow-up observations, and the one candidate that had an orbital estimate calculated by Brown was found to have the wrong orbital inclination. The Vera C. Rubin Observatory, now conducting full science operations, represents the most capable instrument yet deployed for the direct search. Its probability of detecting Planet 9 within a few years of operation, if the planet is at the currently estimated parameters, is in the range of 70 to 80%. The answer may come soon, or it may continue to elude. The outer solar system is large, the planet is faint, and patience has been required throughout the history of this search. But the tools available now are qualitatively better than those available when the prediction was first made in 2016, and the prediction itself is better constrained. What remains certain is that something is happening in the outer solar system that the standard model of 8 planets does not fully explain. The nature of that something is what the next few years of data will reveal. One of the more persistent questions in the Planet 9 story is whether the planet was always there, or whether it arrived later. The standard scenario, as Batygin and Brown originally proposed, involves Planet 9 forming in the inner or middle solar system and being scattered outward by a gravitational encounter with Jupiter or Saturn. This is an ejection from within. The planet started close and ended up far away. An alternative scenario involves capture from outside. During the Sun's early life in its birth cluster of stars, close encounters with other stars were more frequent than they are today. If a star passed close enough to the Sun, the gravitational interaction could have transferred objects from the passing star's system to a bound orbit around the Sun. A planet from another star, captured in this way, could plausibly end up in a wide, eccentric, inclined orbit around our Sun. The foreign origin would explain some features of Planet 9's predicted orbit that are not perfectly reproduced by the ejection scenario. Distinguishing between these origin stories from Planet 9's orbit alone is difficult. The dynamical signatures of ejection and capture overlap significantly. The composition of the planet, if it could somehow be measured, might provide a clue. A planet that formed close to our Sun in the same era as the other planets would have a specific compositional signature, while a planet captured from a different stellar system might have a somewhat different one. But at current distances, compositional measurement is not feasible. The capture scenario, while less mainstream than the ejection scenario, highlights how interconnected the history of the solar system is with the stellar environment through which the Sun has travelled. The solar system did not form in isolation. It formed surrounded by hundreds or thousands of sibling stars in the same molecular cloud, stars that were much closer than any star is today. During that early period, the gravitational environment was very different from the isolated calm of today's solar neighbourhood. The fact that this history might have left a planet-sized trace in the outer solar system, captured from a sibling star, is a reminder that the solar system's history is more entangled with the broader history of star formation than the planetary diagram on a classroom wall suggests. The infrared signals that gave this script its title are easy to overstate and easy to understate. Overstating them would mean treating the 2025 IRAS-Akari candidate as confirmation of Planet 9, which it is not. One unconfirmed source that appears to be moving in the right direction at the right speed, but whose calculated orbit is incompatible with what Planet 9 should be, is not evidence that Planet 9 has been found. It is evidence that something was in a particular part of the sky twice, 23 years apart, and that something might be a distant solar system object. What kind of object is not yet known. Understating them would mean dismissing the result as noise. The Fan et al. Team was careful, methodical, and transparent. They started with millions of sources and applied well-reasoned selection criteria to arrive at one candidate. The fact that one candidate survived stringent filtering is itself meaningful. The fact that it has an anomalous orbital inclination if it is at the distance claimed is also meaningful, though in a discouraging way. The right relationship to this signal is the one that science itself requires. Take it seriously, follow it up, and let the evidence decide. The follow-up observations that would confirm or refute the candidate have not yet been published. Until they are, the candidate exists in the uncertain space between signal and noise, between hint and discovery, between something and nothing. That uncertain space is where the most interesting science happens. It is where questions are still open, where the data has spoken but has not yet said everything it has to say, where the search continues. There is a particular quality of this kind of scientific moment that deserves acknowledgement. Scientists are looking for a planet that may have been orbiting our own solar system for 4 billion years without being known, not in some distant galaxy, not even in a nearby star system, in our own home system. At distances that, while enormous by any human measure, are within the gravitational reach of our Sun. A world that has been there through all of Earth's geological and biological history, through the rise and fall of every species that has ever lived, through the entire duration of human civilization, orbiting slowly and silently in the dark. The infrared signals from the IRAS and Akari data are whispers from that darkness, faint heat signatures from something cold and distant, showing up in 40-year-old data collected by a satellite no longer operating, moving slowly between the 1983 image and the 2006 image, hinting at the presence of something that has always been there, whether those specific signals are Planet 9 or something else. The search they represent is one of the more searching things astronomy has done. Looking for a planet in your own solar system, in data from old satellites, through careful analysis of numbers that correspond to faint infrared light, is not the glamorous image most people have of planet discovery, but it is what this particular search actually looks like. And somewhere out there, in the darkness beyond Neptune and the Kuiper Belt, beyond the scattered disk and the inner Oort cloud, there may be a world waiting to be found, not because it has been hiding deliberately, but because it is cold and dark and very, very far away. There is a final piece of context that makes the 2025 state of the Planet 9 search feel genuinely significant, and it involves the convergence of theory and technology at a specific moment. In 2016, when Batygin and Brown published the original prediction, the instruments capable of testing it decisively did not yet exist. The Vera C. Rubin Observatory was years away from completion. The IRAS and Akari archive had not been thoroughly mined for Planet 9 candidates. The catalogue of extreme trans-Neptunian objects contained only a handful of relevant objects. The statistical analysis was compelling, but based on small numbers. In 2025, the situation has changed in almost every dimension. The catalogue of relevant objects has grown. The statistical analysis is more robust. The orbital parameters have been refined. The infrared archive has been searched specifically for Planet 9's thermal signature and found a candidate. A second independent infrared search has been completed. The Vera C. Rubin Observatory is operating. This convergence is not accidental. It reflects the normal progress of science at the frontier, where each new development creates opportunities that did not exist before. But the coincidence of timing that the instrument most likely to settle the question definitively became operational in the same year that the most concrete observational hints appeared gives 2025 a particular weight in the Planet 9 story. The next few years will almost certainly produce either a confirmation or a deep enough non-detection to force a rethinking of the theoretical picture. The waiting will not be much longer, and the answer, whatever it turns out to be, will change our understanding of our own solar system in ways that have not happened since the discovery of the Kuiper Belt, or since Pluto was reclassified, or since the first giant planets were found orbiting other stars. The outer solar system has been speaking in whispers for years. The infrared signals from 2025 are the latest whisper, and the tools that might finally let us hear what it is saying are now pointed at the sky. Stand outside tonight and look at the sky. The planets you can see with your eyes, those bright steady points that do not twinkle the way stars do, are the inner solar system. The ones your grandmother could name, the ones on the classroom poster, the ones with missions named after them. Mercury, Venus, Mars, Jupiter, Saturn, beyond them, barely visible without a telescope, Uranus and Neptune. 8 worlds in a relatively compact arrangement, all within 30 astronomical units of the Sun, all in the same broad plane, all ancient and familiar by now. But compactness is relative. The solar system does not end at Neptune. It extends in various senses much farther. The Kuiper Belt runs from about 30 to perhaps 55 astronomical units. Beyond it, the scattered disk. And beyond that, the zone where Planet 9's orbit would take it, from perhaps 200 astronomical units at closest approach to perhaps 370 at farthest. And beyond that, the Oort cloud, stretching perhaps to 100,000 astronomical units. The solar system in gravitational terms is far larger than any classroom diagram has ever shown. Planet 9, if it is real, occupies a zone that is empty in the current map. A zone between the scattered disk and the inner Oort cloud, where no major body is currently confirmed. A zone that represents an enormous volume of cold, dark space that has never been directly photographed by any telescope with sufficient sensitivity. But beyond them, in the direction of the outer darkness, in the region of the sky toward Eridanus and beyond, there may be a frozen world on a slow, lonely orbit, too cold to shine by its own fire, too distant to reflect more than a whisper of the sun's light, detectable only by the faint warmth of its own ancient heat, glowing in wavelengths no human eye can see, shifting slowly against the background stars over decades. Astronomers in Taiwan found a signal in data 40 years old. Astronomers in Japan confirmed a similar method using even more sensitive data. And when the orbital math came back, the answer was not what anyone hoped. But the search is not over. It is entering its most powerful phase. The largest survey camera ever built is now photographing the southern sky every few nights, going deeper than anything before it. Whatever is out there, if anything is out there, is running out of places to hide. The search has been long. It is entering its most capable phase yet. Good night.